Good morning. Our project constitutes the design and development of a test fixture for temperature and pressure sensors. Our group consists of Giannis Come, Danilo Delgado, and me, Sara Patiño, and our advisor is Sabri Tosunoglu. This is the outline by which we'll run our presentation. We will start off with problem statement and go on to conclusion and future work. Problem statement. Harvard Company is our sponsored company, and this company has asked us to create a test fixture that will be allowed to be used for their pressure and temperature sensors. So in order to do this, we have to validate our results by the collection of experimental data, and after that we have to create our calibration table that will be able to be used by the company in an easy and practical way. The motivation, as established before, Harvard would be our sponsored company, so we want to allow them to have reliable and accurate products. We must consider that their intent is to extend the quality of life, and by contributing to their project, we will also be extending the quality of life of many individuals. We also want to design a product that will be flexible, and aside from the medical field, it can also be applied to other fields. For the objectives, the sensors that the company has provided us is of cylindrical shape, and it has a diameter of 2 millimeters and a height of, a diameter of 70 millimeters and a height of 2 millimeters, so it's quite small. And then we have to collect all the experimental data using one of the designs that we have proposed. This will be done through optimization. We'll create several alternative designs, and the best design will be reproduced finally. So we'll have to collect all experimental data in terms of pressure and temperature, and after that we will be doing our calibration table. This will be done in terms of pressure and temperature. For the pressure range, we have a -10 to 200 millimeters of mercury, and for the temperature, we have 20 to 60 degrees Celsius. It must be noted that between the 20 to 60 degrees Celsius, we have the 37 degrees Celsius, which constitute physiological conditions, and in this specific temperature, we'll be concentrating most of our work. The 60 degrees boundary constitutes the sterilization temperature of the company. The company has also asked us to have an accuracy for pressure of 1 millimeter of mercury and for temperature of 0.1 degrees Celsius. After that, we have to support our results with engineering work and computational analysis. And concerning the cost analysis, the company has given us a budget of $5,000, and so we will have to stay within that boundary, but as of now we have 3,200, and the advantage that we have is that we are allowed to use all the laboratories from the company itself.
Hello. The following items that I will be discussing will be part of possible options that we will be using towards our designs, and also part of our literature survey. As for the temperature measurement devices, we have the thermocouple, the resistance temperature detector, and the DAC system. The thermocouple is a device that once it senses a change in temperature, it produces a voltage, and then with that voltage, you use it alongside a thermocouple calibration table, which is then calculated with a temperature. And then the resistance temperature detector is based on a principle called thermal resistivity, and the DAC system is pretty much the microprocessing unit of the fixture, and what it does is that it reads an input and then produces an output, which you can readily see. As for the sensors, these are some of the sensors that we are also thinking about possible options in obtaining in our fixture. The MEMS sensors we are definitely thinking about because of its wide variety in sizes and specifications. As Sarah mentioned earlier, we need our sensor to be a diameter of 7 millimeters and a length of 2 millimeters, and we need it to be a cylindrical shape. And here you'll see a figure of a dual element sensor, which you'll see later in alternative designs, and it provides a 65% reduction rate in measurement risk, and because of that, due to that, it provides redundant measurements, which then provides a hot backup. As for pressure measurement, here are some of the devices that we're also thinking about: the potentiometric and the resonant wire. We need to make sure that whichever device we end up using holds in the pressure range of -10 and 200 millimeters of mercury. And here we have some of the standards that we will be including in our design project. First, the weathering of reference materials. That's when we select one material, and then we keep that constant, vary other materials, and see how the fixture either progresses or fails. As for the temperature calibration, we will be using that standard to set up our calibration table for the air and liquid mediums. And as for the uncertainty of test results, that goes ahead and defines uncertainty and how it's used and obtained in our test results. Here we have for the global learning. We want to make sure that the materials that we're using are compatible in other countries besides the United States. We want to make sure that our user manual is in English as well as Spanish and maybe possibly translated in other languages. The dimensions and specifications, we want to make sure that they're in SI units as well as English metric system. And then as far as the environmental aspects, we want to make sure that there's very little hazardous waste, if any, barely minimal amount of leakage, and the materials, we want to make sure that they're as environmentally and economically friendly as possible. Here you see our Gantt chart, which is pretty much a timeline of how we want to run through our tasks. Right now, we're in the consideration of alternative designs, and during the summer, we want to pretty much finalize which design we want to choose, and then to final production. Here we have our subdivision responsibilities, where we have our tasks, and then the individuals that are working on it. Most of them where we have all three of us, we're all working together, but there's mainly one leader that makes sure that the tasks are completed and performed as efficiently as possible.
Yeah, so also, referring back to what Janice and Sarah mentioned, we actually, what we want to do is we want to test for both pressure and temperature. Ideally, would be to test for both together, which that's what we want to get to. For our certain design alternative, what we're going to do is we're going to test for temperature first. The way we test for temperature, what we would want to acquire is using liquid, we want to have an inlet of either hot or cold water, or the mixture of both. And then with the mixture of both, we want to have the required temperature inside the chamber. And then using dual sensing elements, sending back to our transmitter, basically acquire that information and record that information. So we can see how the pressure sensor that we're actually testing works in that specific temperature and that liquid that we're using. For our second design alternative, we want to test for pressure. Using the same thing I was saying, it's liquid. We want to test the inlet and the outlet, and using between the inlet and the outlet flow of the water, we want to acquire the specific temperature pressure inside the chamber, and then using that pressure, we want to test how basically how the sensor reads, how it portrays the information, and how much information it feeds back, and what information it actually reads us. In order for us to acquire that as well, we want to test for both realistic and experimental data. Using that, we want to use a separate sensor that we want to input into the chamber in order for us to test between the two differences. For our third design alternative, what we want to do is we want to combine both. So in order for us to combine both, we came up with an idea where we want to have a chamber housing the sensor. And then in order for us to acquire pressure, like I said before, we have a water pump, and then we have an outlet between the water tank reservoir. Now, in order for us to control the water pressure, we want to have the water pump, which is the inlet, and then an outlet valve, so we can control the difference between the outlet going out and the inlet coming in as well. And then in order for us to acquire the temperature, we want to have both a hot water reservoir and a cold water reservoir. Those two are connected to a valve control system, which allows us to mix the two in order for us to acquire the right temperature. And then in order for us to validate everything, make sure everything is running, just in case we have any issues, we also want to have sensors in between, for example, the water valve and the water pump to make sure that the water that's coming in is the water that we actually expect us to acquire the temperature. In order for us to make sure everything is going good, we have it connected to a DAC system. The DAC system is supposed to allow us to have the system basically self-calibrate and self-adjust itself on top of the person, the actual user, actually have the option to be able to calibrate the system as well and adjust if there's any irregularities inside the actual system. So in conclusion, what we want to do is we want to make sure we test as much as possible. We want to make sure we grab as many readings and as much recording as possible, because the company acquired us in order for them to basically get the test the system and to get the patent for anything they need. They basically got to validate all the information that is acquired. So they want us to test as much as possible and to acquire as much information as possible. In order for us to do that, we want to experiment and optimize the best design and make sure that everything is going good and we're running good. We want to manufacture the rig. We want to generate calibrated table and temperature pressure ranges. And then they want us to do simulations. In order for us to do simulations, we want to do simulations both using MATLAB and SolidWorks, and then using thermal analysis, static analysis, and flow analysis. The main thing here is they want us to get as much information as possible to basically test and validate our system. And here we have those.
Thank you.
Questions?
I'm kind to absorb it all in. Besides doing the simulation using MATLAB and SolidWorks, are you gonna try to back up your numbers by hand calculations to confirm that those are correct?
No, of course, but one of our main things, for example, like I was saying earlier, we have the chamber, right? We'll have different, pressure sensors, basically pressure readings and temperature readings. And the way we want to really validate that, as I was saying earlier, is we want to have the sensor inside the chamber and want to be able to introduce a second sensor. So we have to test for realistic and experimental data. We want to make sure that the temperature that's reading inside is the actual temperature inside. And if it isn't, we want to make sure that we can read that in order for us to calibrate it enough so we can have the right reading. We want to basically optimize and calibrate as much as possible for us to acquire the right amount of data and the correct data, because we want to have as minimal amount of error as possible.
And as far as the hand calculations, we want to pretty much use, I guess, the equations that we have acquired from fluid dynamics and also classes like thermodynamics, where it uses like the changes in pressure, in temperature, and definitely implement those in our results.
Yeah, the only reason I say that because I've seen the first part and the second part, and a lot of times the students tend to rely on the software, and we ask them, well, have you done the calculations to confirm it? And they're like, okay.
No, that's one of the other things too. Like, the company wants us to basically show as much information as possible, because at the end of the day, in order for them to get the system or the sensor approved to be able to apply it in any field,
Right.
you got to validate it.
Right.
So they basically want us to provide as much information as possible, and that's what we were trying to do for the design of turn groups. They want us to do, if we can possibly, do 3 different designs. We do one for pressure, optimize that one as much as possible, one for temperature, optimize that one as much as possible, and then after that, combine the 2 and then optimize that one.
Yeah, quick question. Is the test fixtures, I guess, real purpose is to have, let's say for hardware, some type of all-in-one test bank where they can just go in and get any pressure or temperature sensor and use it for whatever application they want? So, and that's really good. That's really nice to have actually in our lab. Sometimes, we don't have a sensor, we have to get it. So if that's the final approach, which is, that's amazing, that's great. On design alternative 3 then,
Yeah.
I suggest that you do have this control of the temperature by mixing two.
Okay, yeah.
So if that's not necessary to as far as the end result,
Okay.
then consider that in your project. This might be over designing. You can just heat the water accordingly to test your
Yeah, of
sensor,
course.
So try not to kind of overdo things for your
Okay.
project and.
Of course.
Thank you.
All right. Thank you.